Okay, thank you for coming along to this meeting of the AI Institute. I'm Professor Ron Van Maiden. Before we start, I'd just like to give an acknowledgement of country. So I'd like to show my respect to and acknowledge the Gadigal people who are the traditional custodians of the land on which we're meeting today, and their elders past and present. Our speaker today is Professor Joe Halpern from Cornell University. Joe did his PhD in mathematics, actually, at Harvard, and subsequently worked for a number of years at IBM Almaden, a very distinguished group there in the theory group at Almaden. As I don't remember what year it was, moved to Cornell University quite some time back, where he was a professor in the computer science department. Although Joe's work spans a whole lot of disciplines, there's been an increasing amount of interaction between computer science and philosophy, particularly logic, and also economics more recently. Joe has been one of the drivers of building those connections, and his talk today will touch, I think, mostly on the philosophical aspects.
It's true.
So hand over to Joe.
Okay, thanks, Ron. I should say this talk is meant to be mainly audience participation. Feel free to ask questions. Don't wait till the end. Although since I really do, I'm supposed to end at noon, I might say take it offline. But especially in an audience this size, do by all means ask questions. So defining causality is hard. And the nice thing this talk, I can say, people have been trying for literally thousands of years. So let me say that the philosophers have distinguished two kinds of causality. One is what they call type causality, the other one's token causality. So type causality is like smoking causes cancer. Token causality is the fact that Maury smoked for 30 years is why he got cancer. Sorry, Mark. So the law is certainly really interested in token causality, right? Because they're looking at specific people. So, why should we care? So this is by way of distinguishing the two notions. They're clearly related. But I might say, well, look, it's true that it was pouring rain last night. It's true that I was drunk. But the cause of the accident was the faulty brakes. That's why I'm suing GM. Right? So in terms of type causality, bad weather, pouring rain causes accidents. Drunk driving causes accidents. But I want to say in this particular case, it was neither the drunk driving, I drive great when I'm drunk, nor the bad weather, it was the faulty brakes. So that's token causality as opposed to type causality, right? So as I say, actual causality, token causality comes up everywhere in the law. Statisticians care about token causality. They tend to be more concerned with type causality, but anyway, I'm going to argue it's also relevant to computer science at the end. But the focus of this talk is just, first of all, defining it. That turns out to be hard. So people have tried literally since Aristotle. So it's great. In computer science, the classic results were like 20 years ago. Even 10 years ago, it was like an old result. In philosophy, the classic results, they were millennia ago, right? So the work, arguably it was David Hume who started the modern view of causality, but really the definition I'm going to focus on is due to David Lewis, who's a very famous philosopher, passed away a few years ago. And the idea is to use counterfactuals. So the idea is that A is a cause of B if it's the case that had A not happened, B wouldn't have happened. So me doing this caused the bottle to fall over. Had I not hit the bottle would not have fallen over. So we want to say I'm the cause, because had I not hit it, it would not have fallen over. Does that make sense? And so, if the brakes I'd like to say, if the brakes hadn't been faulty, I wouldn't have had the accident. That's why the brakes are the cause. And I'd like to say, even had I been stone cold sober, I still would have had the accident. The fact that I was drunk was not the cause. Right? Again, does that make sense? So this is what the law calls but-for causality. But for A, B wouldn't have happened. And if that's all there was to causality, I could end the talk now and I wouldn't have had much of a career studying causality. So it turns out that, it's actually tricky. UniPearl, this is the Pearl Innovation Networks, who has been working on causality now for well over 20 years, gave a definition of causality. And now the trouble with this, so Ron mentioned I have a PhD in math, and my basic temptation was give a definition, prove it's correct, right? I mean, prove some theorems. And the trouble is that I don't, it's not that I tried to prove the theorem and failed, it's I didn't know how to state the theorem. What would it mean that I had the right definition? So what we did is what philosophers have been doing for a long time, decades, centuries, depending on how you count, is because the philosophers have been looking at it for so long, they have many, many examples that were designed to shoot down previous definitions. That's what they're good at, among other things. And so what we did is what has been traditionally done in the philosophy community is we showed that our definition dealt with all the previously known counterexamples perfectly well. And that's what we did in our paper. Now the trouble with that approach is that, well, yeah, but somebody else will come up with now that your definition's out there, they'll come up with a counterexample to your definition, and that happened. And the someone who came up with it was actually a student of Pearl's, Max Hopkins. So we came up with a new improved definition, i.e. corrected the first one. And that appeared in the British Journal of Philosophy of Science in 2005. And then there's a whole story behind this that I won't go into. I came up with yet another definition, which was simpler and seemed to have all the properties of the first two, all the good properties. In 2015, that's what I'll be focusing on here. But let me admit, it is possible that somebody will come up tomorrow and construct a counterexample. Now, what counts as a counterexample? Well, typically it's an example where we all have strong intuitions about causality, and where we all agree that you want to say that A is a cause of B, or you don't, depending on which way the counterexample goes. But my definition does the wrong thing, right? It calls it a cause when our intuition says it shouldn't be, or vice versa. This is exactly the counterexample that Max Hopkins came up with. It qualified as a counterexample because both you and I looked at it and said, yes, we're saying that A is a cause of B, and no, it shouldn't be, right? So we patched the definition, and the second definition was a bit more restrictive and solved that problem. So, and it really is the case that, I feel like I'm walking around with a big target because philosophers really are trying to shoot down this definition. This definition is now widely known in the philosophy community. So far, I don't think they've succeeded. I mean, I guess that's a matter of, they might not agree, but I don't think they've managed. But as I say, it is possible somebody will come up with a counterexample tomorrow. I can't prove otherwise. I wish I could. So let me explain why it's not so easy. Why won't the simple but for work? So this is an example due to David Lewis. Started the ball rolling with counterfactuals. And the story is the following. So Billy and Susie pick up rocks and throw it at the bottle. Susie throws maybe a teeny bit harder, or she throws a millisecond earlier. Anyway, her rock gets there first. It's the one that knocks over the bottle and shatters it. But we can see that Billy's rock would have hit the bottle had Susie's rock not hit it. I mean, we have video. We can see that Billy's rock sailed over where the bottle would have been had it not been knocked over. Right now, so I would like to say that Susie's throw is the cause of the bottle shattering, not Billy's throw. I think most people would agree. I mean, certainly that's what I want my definition to say, and it does. But the problem is, but for causality doesn't work. Had Susie not thrown, well, Billy's rock would have hit the bottle and it would have shattered anyway. So Susie's throw is not a but-for cause of the bottle shattering, yet we want to say that it's a cause. Are we together? So that's what makes life complicated. That had but-for worked all the time, then we would be done. And by the way, I should say, the law uses but-for, at least in the States. They understand that it's not good enough. They do not have a good alternative. That's the state of causality in American law. And it comes up all the time. So that I can't resist saying, as an aside, so I was the token computer scientist at a workshop with legal scholars and philosophers, and they played us this audio 8 of an American Supreme Court case, and it went something like the following. There was a heroin dealer who sold heroin to this guy, who everybody agreed had serious heart problems and he was going to die like within a day or two anyway. Right? So that was not open to discussion. That was stipulated by both sides. So the guy took the heroin that he had been sold. He died of an overdose of heroin. And the drug dealer was on trial. And this case made it all the way up to the Supreme Court. And of course, the drug dealer's lawyer was arguing there was no but-for causality here, right? Had the drug dealer not sold the drug, the guy would have died in. And you could hear in the background of this tape that Justice Kagan, Eleanor Kagan, an American Supreme Court justice, saying, yeah, it's not but-for causality. They don't have a good alternative. So this is an issue that arises, in quite serious legal cases. It's not just a little story that I like to tell in my talks. This is a big deal. So we'd like to say that in this case, Susie's throw is a cause, Billy is not. And, roughly I'd like to say that given that Billy doesn't hit the bottle, which is in fact what happened, Billy's throw did not hit the bottle. So let's fix Billy's throw at not hitting the bottle. Well, in that case, we have but-for causality. Had, fixing Billy not hitting the bottle, then had Susie not thrown, the bottle wouldn't have shattered, right? Now, why isn't Billy also a cause? Well, I'm fixing something that actually happened. Billy, in fact, didn't hit the bottle. Susie, in fact, her throw actually did hit the bottle. So it's not symmetric. And, intuitively, why isn't Billy so also, duh, as my kids would say, because his rock didn't hit the bottle. But we want to capture that in the formal definition. That's going to be the difficulty. So let me get a little bit formal now, not terribly formal. So the idea, we're going to use what are called structural equations. This is something that has a long history, but that was really formalized by Pearl. The world is described by variables that affect each other. The effect is modeled by structural equations. Actually, let me stop. How many people here know what a Bayesian network is? How many people don't know what a Bayesian network is? All right, so let me say a few words about structural models. Think of a structural model as a directed acyclic graph. There are nodes at the top and have edges going down. And there's no cycles, that's the acyclic. And the intuition you should have is parent is a direct cause of its descendant. Now, for those of you who know Bayesian networks, we again have these directed acyclic graphs. And with every internal node, there's what's called a conditional probability table. So the probability that x equals 3, conditional on its parents' values, conditional on y equals 0 and z equals 1, and so on. Here, rather than having a conditional probability table, we're going to have equations. So I'm going to call the variables at the top of the directed acyclic graph exogenous variables. Their values are determined outside of the scope of the model. All the ones that aren't at the very top of the directed acyclic graph, all the external nodes, for each of them, there's an equation that will give the value of this variable as a function of the values of its parents. So I'll have an equation that says x equals y plus z. So y and z are parents of x. Once I know the values of y and z, that'll determine the value of x. And these are deterministic equations. They don't have to be nice in terms of plus and times. I mean, they can be arbitrary. But they're equations and the intuition, why do I have this? Using this kind of a model allows me to model the effect of interventions. So if I were to intervene and set y to 3, think of this as an external intervention. This is like the kinds of experiments that ideally economists would like to do with external interventions. Then the model will tell me what happens. If I intervene and set y to 3, then I used to have an equation for the value of y. It told me the value of y is a function of its parents. I get rid of that equation. I just say, okay, there's a new equation for y. The equation says y is 3, right? All the variables below y, they still have their equation. So now that I've set y to 3, if x is a descendant of y, and the equation for x is y, x equals y plus c. Well, okay, I can now figure out the value of x using the fact that y is 3. So these structural equations models, the real motivation behind them was to allow us to model the effect of interventions. If you intervene and set y to 3, it tells you what happens to all the variables below y in the graph, and it has no effect on the variables above y. And again, you should think of the edges in the graph as modeling direct causality, but that's an intuition. So that's what these equations look like. So as I said, the exogenous variables are the ones at the top of the graph, whose values come from the outside, and the endogenous variables, all the other ones, the ones not at the top, they have these equations that gives their value as a function of their parents. And whoops, going the wrong way here. So here's a little bit of formalism, but this is not going to come up in the rest of the talk, so don't get too excited. But let me just say that, so we have primitive events like x equals 3. So capital X is a variable. With each node in the graph, there's an associated variable. And I can say, okay, x is 3. Here's the interesting statement. Read this as saying, after setting capital X to little x, then phi holds. The reason I've got these arrows here is this could represent a vector variable. So I could set x1 to 3 and x2 to 7 and x3 to 5. After doing that, phi holds. So the intuition is that I'm performing an intervention. I'm intervening and setting x to 3 and asking, well, okay, after I've intervened and set x to 3, what happens? Phi is one of the things that happens. That's how you should read this. Does that make sense? And then we close off with conjunction negation. It's just fun. So formally, a model consists of a bunch of variables, and you have to tell me which ones are exogenous and which ones are endogenous. And that's a real modeling choice. I'll have an example, actually, at the very end of the paper, where different people will make different choices as to what counts as exogenous, what counts as given, so to speak, outside of the scope of the modeling exercise, and what you're going to view as endogenous, the variables that you can do something about. And for every endogenous variable, there's a structural equation that gives the value of that variable as a function of its parents. Okay, that's what a model is. And of course, different people could take the same situation and model it quite differently. So the definition of causality is going to be given relative to a model. And if we disagree about the model, we might disagree on whether A is the cause of B. All right, that's perfectly okay. So what's the semantics here? So again, think of, you've got this directed acyclic graph. Once I set, so the U is a setting of the exogenous variables. It tells me the values of all the variables at the top. Well, given the equations, once I've told you the values of the variables at the top, that forces the values of all the variables in the deck, right? Because I've got the equations that says, okay, once I've got the top stuff, that tells me the next layer and the next layer and the next layer. Everything else is forced by the equations. Again, these are deterministic equations. So it makes perfect sense to say, look, once you've told me the values at the top, is y equal to 3? Well, yeah, if it's the solution to the equations, given the context, given the setting of the variables at the top of the exogenous variables.
Is uniqueness an important part?
Sorry?
Is that important that that has to be a unique solution?
It will be unique here if I were to allow cycles, and I do in the appendix of the paper, then it's actually not unique. There are technically multiple fixed points. It is important here, so to address your question, that otherwise, what would it mean to say y is 3 if there wasn't a unique solution? If y could be either 3 or 5, then here I want to say, look, if you set the variables at the top this way, y is going to be 3, because there's only one thing y can be. So I would have to change the semantics here if there wasn't a unique solution. So it actually is important that there's a unique solution.
But could you generalize this if you said y is greater than 3?
Oh, sure. I could, and in fact, as I say, once we allow cyclic models where A can influence B and B can influence A, there will, in fact, it won't be unique. We'll lose this uniqueness And you have to think about, so you might be able to say, well, y is greater than 3, because in all solutions, y is greater than 3. But in general, I mean, especially when you get to this next clause, you have to be a little bit more careful. Let me not go into that, because all of the examples literature, and I really mean all of them, they're acyclic. And so this issue doesn't arise. So what do I mean when I say, when I intervene and set x to 3 phi is true? Well, then I'm just looking at a new model, which does this, which is just like the old model, except I used to have an equation for x. I throw out the equation for x that I used to have. It used to be like x is y and z, or whatever its parents are. And I just replace it by a new equation. This is x is 3, independent of its parents. X has become like an exogenous variable because its values are determined. So now I have a new model. It's just like the old model, except I've replaced the equation for x. And I can say, okay, in that new model, is phi true? It either is or isn't. And if it is, then I'll say that this statement, after setting x to 3 phi is true. And so, I might, if I'm an economist handing out mosquito netting and asking, does that improve the situation for malaria, right? That economists care about things like that. So if I've set people getting mosquito netting to 1, think of that as the variable x. Do fewer people get malaria? So, phi would say something like number of people getting malaria, that's a variable, is less than, 3% or something, or whatever, right? So you could ask, what's the effect of this intervention? Well, of course, that depends on the model. And, economists, how does the world work? When you do this intervention, does that, does handing out mosquito netting lower the incidence of malaria? The answer is apparently yes, but it works better if you charge for it. So, people have some skin in the game. So we can debate what the causal model should look like, and whether or not handing out mosquito netting improves the amount, the incidence of malaria, will depend on the causal model, about which people can disagree. And of course, that's why they're doing experiments to figure out how causality works in the world, right? So
we need to understand the x's as types or tokens here.
they're variables, so they're definitely not types in the programming language sense or anything like that.
It's not really about mosquito netting, it's mosquito netting here and now for this person.
Oh, I see. Yes, you'd have to specify what you mean, right? So it's up to the modeler to say exactly what does it mean that this variable has value 3. Do I mean that, for this particular person, if x represents height, well, that's sort of meaningless. What does it mean to say height is 6 feet? No, I have to say the height of this particular person is 6 feet at this particular time, because I guess we shrink as we get older, as my kids point out to me. So yes, but this is up to the modeler to specify what the variable means, right? The abstract framework is completely silent. It just says there are variables, they have values. How do we understand what it means that x equals 2? Well, that's your problem as a modeler to explain it. And it is a serious problem. Let me not try to minimize it, but it's, so to speak, beyond the scope of the formal model to explain what it means that x equals 2. That's the job of the modeler. And it is a very important job. I really don't want to minimize it. So let me just give you some key examples. So you have 2 arsonists dropping lit matches in different parts of a dry forest, and both cause trees to start burning. And you can imagine what I'll call the disjunctive scenario, where the forest is really dry, and one match would have been enough to get the whole forest blazing. And the conjunctive scenario, you need the conjunction, is when both matches are necessary to burn down the forest. Okay, so we can describe both of these scenarios using this really thinky causal network. This is the acyclic graph. So we have an exogenous variable that determines whether or not these guys drop matches. Who knows why they drop matches? They were brought up in a household where dropping matches was fun, beyond the scope of the model. So we have 2 variables, ML1 and ML2. ML1 says the first arsonist dropped a match, yes or no. So it has 2 possible values, 0 or 1. Likewise, ML2. And this variable says the forest burns down. And what's interesting here, so I'm going to assume that the values of ML1 and ML2 are determined by you. So, tell me what happens outside. I'll tell you whether the guys were drop matches. But the equation for FB will depend on whether I'm looking at the disjunctive scenario or the conjunctive scenario. So FB is either ML1 or ML2. If either guy drops a match, the forest burns down, or ML1 and ML2, both guys have to drop matches before the first forest burns down. They're just two different models, right? That they agree on everything except the equation for FB, and the equation for FB, of course, will let you capture whether you're in the conjunctive or disjunctive scenario, right? I still owe you a definition. That's the whole point here. What it means to say that A is a cause of B, given a model and a context. So intuitively, what I'm defining A as a cause of B, I'm assuming that all the relevant facts are given. So the structural equations model tells me, how does the world work? What are the equations? You know, does smoking cause cancer, right? If you smoke for a long time, do you get cancer or not? Well, that'll be part of the model. And it also tells me the context. So think, you know, it'll tell me, did one guy drop a match? Did both guys drop a match? Did neither drop a match? That'll be in the context, right? So there's no uncertainty here. I'll talk about probability shortly, but so far there's no uncertainty. And the things, the A's, the things that can be causes, I'm going to restrict to conjunctions of primitive events, like the fact that X1 is 3 and X2 is 5 and X3 is 8. That can be a cause of something. And the fees, the B's here, what can be caused are arbitrary Boolean combinations of primitive events. So, okay, here's my definition of causality. It has 3 clauses. All 3 papers that I talked about had the same 3 clauses. They only differed in the middle clause, which I'm going to punt on in this slide. So the first clause just says, I would never say that A is a cause of B unless A and B were both actually true. So I wouldn't say that, you know, Susie throwing a rock caused the bottle to shatter if Susie didn't actually throw a rock and the bottle didn't actually shatter. That's just not how we use the notion in English, right? So there's no way I'm going to say X equals X is a cause of phi unless it's the case that both X equals X and phi is true. This is non-controversial. It's just, I'm saying that's just the way we use the word causality in English. We never say that A is a cause of B if A and B don't happen. The second clause is complicated. That's going to be the whole next slide. And the third clause, again, is quite non-controversial. It says that X, remember X is a conjunction of things, is minimal. There are no irrelevant conjuncts. So I'd like to say, look, Susie throwing a rock, it caused the bottle to shatter. Maybe she also sneezed. I don't want to say that Susie throwing the rock and sneezing caused the bottle to shatter. The fact that she sneezed is irrelevant. So, but it would still say, if she actually did sneeze, it'll turn out that AC1 and AC2 will both hold. And I want to say, yeah, it's still not a cause. Get rid of the fact that she sneezed. Right? So AC3 is this minimality condition. So AC1 and AC3 are not controversial. All the action happens with AC2. Let me talk about AC2, which, as I say, changed from paper to paper. So in the original definition, AC2 was quite complicated. You might still think it's complicated, but trust me, it's much simpler than it used to be. So here's the definition. So the way to think about this is, first, this is W, forget the W. Then we have the pure counterfactual. I'm going to say capital X being little x is a cause of B. Now, but for, if X were something else, if it were X prime, then phi wouldn't happen, not. Right, so if you ignore the W, this is literally the but-for definition, saying that the fact that X equals 3 is a cause of phi, because had X been 2 rather than 3, had it been something else, phi would not have happened, right? That's what this is saying. So I'm going to extend the but-for, which I have to do to deal with Susie throwing rocks. So I'm saying that I'm allowing there to be a set of variables. This is existentially quantified. The set could be empty. If the set is empty, we get but-for. So there is some set of variables W and an X prime, you know, an alternate setting of X, such that if you fix W, capital W to little w, and capital W is little w in the actual world. So I'm gonna hold fix the fact that Billy's rock did not hit the bottle. In the actual world, Billy's rock did not hit the bottle. That's my W. The capital W is did Billy's rock hit? Yes or no? And the little w is no, it didn't hit. I'm going to keep that fact fixed. And then I'm going to look at the counterfactual. So keeping fixed the fact that w is little w, which is what's true in the real world. That's what this clause says. In the actual situation, capital W was in fact little w. Keeping that fact fixed, now changing capital X to little x prime results in phi not being the case. So as I say, a special case of this definition is where W is the empty set, and then we recover but for causality. So this is generalizing but for causality. Does that make some sense? This will be clearer when I give you examples. So hang on to this. So let's take a simple example. The arsonist, so there the W is empty, so it is simple. So let's first take the conjunctive case where it needs both matches to get the forest fire burning. So then I'd like to say each arsonist who dropped a match is individually cause of the forest burning down. He's a but-for cause. Had arsonist 1 not dropped a match, the forest would have burnt. Had arsonist 2 not dropped a match, the forest would have burnt. So each one separately is a cause. There can be more than one cause of an outcome. That's the case here. There are 2 causes, right? And that I'm hoping seems pretty intuitive. More interestingly, the disjunctive scenario, where you only need one match, it's the conjunction that's a cause, which might seem a bit strange, but you need to change both in order to get a different outcome. That's what's going on here. What's interesting, I'm not going to get into it in this talk. I have another talk and explanation. I have another notion called sufficient cause, and that actually works more the way you'd expect, that a sufficient cause for the outcome in the conjunctive case is that both of them drop matches, because that suffices to get the outcome and anything less doesn't. And in the disjunctive scenario, each one of them separately is a sufficient cause, because either one can drop the match. And so it's interesting that actual causality works just the opposite way from sufficient cause in this example, right? That in the conjunctive case, each of them individually is an actual cause, but it's the conjunction that's a sufficient cause. And in the disjunction case, it's the conjunction that's the actual cause, but each one of them individually is a sufficient cause. There are different intuitions that I think they're both reasonable, but this is the one we care about in the law. So let me go with this one, but let me talk about Susie and Billy, and you'll see why I need the complications of the double. So I want to model Susie and Billy throwing rocks at bottles. Here's a naive model. We have 3 variables. Susie throws, Billy throws, and the bottle shatters. And let's bake into the model the fact that they never miss, right? So I'm going to make the equation for BS, bottle shatters, not anything else. I'm going to make the equation for BS, either ST is 1 or BT is 1. If either one of them throws, the bottle shatters. So again, I'm baking in the fact that they never miss. Now this model is completely symmetric. Both Billy and Susie are causes, right? And I claim this is just not a very good model, because it treats Billy and Susie symmetrically, and my story didn't. In my story, I said Susie throws a bit harder. She hits, her rock hits the bottle. Billy's rock does not. This doesn't capture. So let me give you a more complicated model. There's more than one way to do this. This is, one of many. I don't want to claim this model is unique, but I'm going to add to this model 2 more variables. Susie hits, that is her rock hits the bottle. Billy's rock hits the bottle. And again, I'm going to bake into this model, I absolutely don't have to, just for simplicity, the fact that Susie hits first, and if she hits first, then Billy does not hit. So the equation for BH says Billy's rock hits the bottle if Billy throws and Susie's rock does not hit the bottle. Because if Susie's rock hits the bottle, then the bottle gets shattered, and Billy's rock doesn't hit the bottle because there's no bottle there to hit. Okay. So the equation for BH is 1, Billy's rock hits the bottle if BT is 1, if he throws, and SH is 0, Susie doesn't hit. The equation for SH is Susie hits, Susie throws. She never misses. And again, the equation for BS is the disjunction. The bottle shatters if either one of them hits. Okay, so this model, it's not symmetric anymore in Billy and Susie. It's given Susie precedence, if you like. It's her rock that gets there first. So this breaks the symmetry. And I claim in this model, which is capturing what actually happened, Susie's a cause, but not Billy. Why is that? Well, Susie's a cause. The definition allows me to fix the fact that BH is 0. In the actual world, Billy did not hit the bottle. So I'm going to fix that. And once I fix that, well, if Susie doesn't throw, the bottle doesn't shatter. If Susie throws, the bottle shatters. So we get the but-for causality. Fixing BH at 0, which is what happened in the world. But notice that fixing it is counter to the equations, because if I hadn't fixed it at 0, if Susie doesn't throw and Billy does throw, then he would have hit, right? So I'm fixing it in a way that violates the equations. That actually turns out to be unavoidable. So with that, Susie's a cause, according to the definition, because if you fix the fact that Billy didn't hit, which he didn't, then the bottle shatters or not, depending completely on whether Susie throws, we get but-for causality. We cannot play the symmetric game with Billy. I can't fix SH at 0, because that's not what happened in the world. This is capturing the well, Susie actually hit, Billy's didn't. I can't fix SH at 0 because the definition only allows me to fix things that actually happened. And it's not the case that it actually happened that Susie didn't hit, right? So I can't play the symmetric game. And it's actually easy to show in this model. Susie is a cause, but Billy is not a cause. Okay. So that's good. That's what we wanted. I mean, good in the sense that the definition is doing the right thing for us. Let me give you a few examples where the definition might not work quite the way you expect. And the first example shows, among other things, that causality isn't transitive. You'd think it was. A cause is, A is a cause of B, B is a cause of C, A should be a cause of C. I certainly thought so until I saw these examples, and the examples are actually pretty convincing. And I think it's fair to say that actually all philosophers agree that causality is not, in general, transitive. I'll say a few more things about that in a second. But so this is an example due to Ned Hall, who's a philosopher at Harvard. So Billy contracts a serious but non-fatal disease. He's treated on Monday, so he's found on Tuesday. Now, had Monday's doctor forgotten to treat Billy, there's a backup. Tuesday's doctor would have treated Billy, and he would have been fine on Wednesday. It takes a day to get better after the treatment, right? However, there's a catch. This is a philosophy paper. Had both doctors treated Billy, he would have been fine on Tuesday, but he would have been dead on Wednesday. 2 doses of medication kill you. Okay. So is the fact that Tuesday's doctor did not treat Billy the cause of him being alive and recovered on Wednesday, given the setting, the context where Monday's doctor treats him? And the answer is yes. I mean, in a simple causal model, so we assume that there's a causal model, there's Monday's doctor treating him. That affects whether Tuesday's doctor treats him. The equation for Tuesday's doctor is treat him if Monday's doctor doesn't. So we're assuming that Monday's doctor left at the patient's bedside some kind of a chart showing what he did. Tuesday's doctor checks, and if Monday's doctor does not treat him, then Tuesday's doctor does. Whereas if Monday's doctor treats him, Tuesday's doctor doesn't, right? So whether or not Tuesday's doctor treats him is, exactly the equation is treat him if the other guy didn't. Does that make sense? And then we have the equation for Billy's medical condition, which is just what you'd expect. I mean, it says if both doctors treat him, then he's dead, fine on Tuesday, dead on Wednesday. If just Monday's doctor treats him and Tuesday's doctor doesn't, then he's fine on Tuesday, Wednesday, so on. So we write down the equation that, the Billy's medical condition has 4 possible values. Here they are, right? He's either okay Tuesday and Wednesday. That's if Monday's doctor treats him and Tuesday's doctor doesn't. He's sick on Tuesday and okay on Wednesday. That's if Monday's doctor doesn't treat him, but Tuesday's doctor does. Sick both Tuesday and Wednesday. That's if neither doctor treats him. And he's okay on Tuesday, dead on Wednesday. That's if both doctors treat him, right? So that's the equation that tells you the value of BMC as a function of its 2 parents, Monday's doctor treating him and Tuesday's doctor not. So what can we say about causality? So Monday's doctor treating him, which is in fact what happened, is a cause of BMC being 0, of him being okay Tuesday and Wednesday, because Monday's doctor treating him caused Tuesday's doctor not to treat him. So, the right thing happens. Okay? Are we together? I mean, that's, a Tuesday's doctor not treating him as a cause of him being alive on Wednesday, or being alive on Wednesday is not being dead. So being either 0, 1, or 2, not 3, right? So, and that's easy to see, because if Tuesday's doctor had treated him, given that Monday's doctor did as well, he'd be dead, right? On the other hand, Monday's doctor treating him is not a cause of him being alive. So A is a cause of B, well, B is Tuesday's doctor not treating him. B is a cause of C, Tuesday's doctor not treating him is a cause of being alive. But A is not a cause of C. Monday's doctor treating him is not a cause of him being alive, because there's nothing that Monday's doctor could have done that would have made him be dead. He did treat him. Had he not treated him, for sure he'd be alive, because it takes both doctors treating him to be alive, right? So changing Monday's doctor, no matter how you fix Tuesday's doctor, is not going to affect whether, is not going to get Billy to be dead. It's easy to see that this happens. So causality is not transitive, nor does it satisfy what philosophers call right weakening. Let me explain right weakening. If A is a cause of B and B logically implies B prime, A may not be a cause of B prime. Here's the counterexample that Monday's doctor treating him is a cause of BMC being 0, being okay both Tuesday and Wednesday. BMC being 0 logically implies the BMC is either 0, 1, or 2, right? The fact he's okay Tuesday and Wednesday implies that he's alive. But Billy's doctor treating him is not a cause of him being alive. So A is a cause of B, B implies B prime, A is not a cause of B prime. Now, David Lewis gave a very influential definition of causality, where he defined one-step causality, so one step in the tree basically, and he defined causality to be the transitive closure of one-step causality, and the effect of that is he baked in the fact that causality was transitive. His notion of causality was transitive. He also baked in this right weakening notion, and as I say, now philosophers agree that that definition is simply not correct. I mean, causality is not like that, but still there's a puzzle here that I certainly felt the causality was transitive before I saw these. There's a whole bunch of other examples like this, and they're quite convincing. But why do we all feel that causality is transitive? So I have a paper that sort of tries to give sufficient conditions for causality that I claim happen a lot. So maybe that's why we think causality is transitive. But anyway, in general, it's not. So here's an interesting experiment. So Josh Snow is in the philosophy department at Yale, but he has an appointment in the psychology department, and he calls himself an experimental philosopher, which means he actually does experiments on people. And here's one of them. So the story is the receptionist in the philosophy department keeps her desk stocked with pens. The administrative assistants, the secretaries, are allowed to take the pens, but faculty members are supposed to buy their own. That's the theory. In practice, everybody takes the pens. So on Monday morning, there were 2 pens at her desk, and an admin, one of the secretaries took one of the pens. Professor Smith took the other one, so there were no pens left. And later, the receptionist needed to take an important message, but there were no pens. Who is the cause of there being no pens? Well, if you look at our definition, they're completely symmetric. There were initially 2 pens. The professor took one. The admin took one. No pens. Who is the cause? You can write down the obvious causal model.
Why took the last pen?
Well, so people do sometimes. So they've done experiments on games of what I would call soccer. Is it soccer here or football?
Soccer.
Soccer, good. So, and they look at, if the score is 2-0, is it the person who scored first who's the cause of the person who scored last? I'll come back to that point. It turns out it depends on how I tell the story. So sometimes it's the last one, sometimes not. What's really, so most people say Professor Smith. When they changed the story to say that, and in the story they were very careful they had variants of it where they varied who took it first and who took it last to show that the effect was not the temporal effect in this case. Because when they varied the story to say the pens are supposed to be for the faculty members because the secretaries have their own source of pens, then they all blamed the secretary. So the conclusion was that the reason they were saying it was the professor was that there was this department policy that said the pens are supposed to be for the admins, and the professor is, so to speak, violating the department policy. Although in practice, now we're very careful to say this, in practice it happened all the time. Okay. So what that suggests is that when people are judging causality, or actually more responsibility, they take into account other things that our definition says totally symmetric, would call both of them the causes. And the way we dealt with this, so this is actually, there's a wonderful quote did a Danny Kahneman. This is the Kahneman who won the Nobel Prize, who his amazing work with Tversky, who also would have won the Nobel Prize had he not died. On how people are not totally, started off the whole field of behavioral economics, but he also studied causality. He's actually studied a bunch of stuff, but now he's looking at things like happiness. And he has a quote in one of his papers with Miller. I'm not familiar with Miller. An event is more likely to be undone by altering exceptional rather than routine aspects of the causal chain that led to it. The way to translate this to my definition, if you're considering various counterfactuals, right? You're saying, think about but for causes. Had A not happened, then B would have happened. The A's, you might have a choice of which A's you change. So had the professor not taken a pen, there would have been a pen there. Had the admin not taken a pen, there would have been a pen there, right? So both of them, if you change it, you'll get a different outcome. But people prefer to undo the thing that makes the world more normal. That makes the world, you want to change the abnormal thing to a normal thing. Now, what counts as abnormal? Well, the claim is in this case, because the rule was that the professor wasn't supposed to take the pen, it's more abnormal for him to take the pen than for the admin to take the pen. So you prefer to undo the professor taking the pen rather than the admin taking the pen. So you call the professor a cause. That's the claim. And indeed, this seems to be borne out by other experiments. And we formalize this by adding people who've looked at things like non-monotonic reasoning and belief revision. This comes from that literature that we added a normality ordering to worlds, that one world is more normal than another. This was part of the model. And that let us define a notion of, an ordering on causes. We could say A is a better cause than A prime for B, because we got A to be a cause by changing a more abnormal thing to a normal thing, right? Because there was this notion of normality in the model, we could make sense out of that. Whereas to get A prime to be a cause, we would change a thing that was already normal to be normal or something like that. So we could give a definition. I won't go into technical details, I'm running out of time, but the definition, as I gave us a graded notion of causality, so that A is a better cause than A prime, which actually captured a bunch of things in human reason, which was nice. Now, I should just mention that, what counts as normal? Well, it turns out lots of things affect the normality ordering. Statistical frequency counts. That the more often something happens in practice, the more normal it is. 3 minutes?
Yeah, we have time for questions.
Oh boy. How about 8? Can I negotiate? So,
Keep going.
the typicality, performance, and normative law count is normal. And people seem to take all these things into account. It seems that things like conformance to a norm, doing the department policy, trumps statistical frequency. Moral obligations trump conformance to a norm, like thou shalt not kill. It's abnormal to kill. But people do have sort of fairly well-developed notions of normality. Let me just say one other brief thing. I'll try to get done. So the definition of causality can be extended to deal with responsibility and blame, among other things. So what I want to capture is the notion that, look, if there's an 11-0 vote, you want to say the people who voted for, don't blame me, it would have happened anyway. They feel less responsible than in the case of a 6-5 vote. That's the intuition I want to capture. And the way we capture that roughly was to say, I won't go into technical details again so that I can finish on something big that was up in time. But in the case of the 6-5 vote, each of the people are critical. If they change the vote, that changes the outcome. In the case of the 11-0 vote, nobody's critical because you change the votes 10-1, right? It takes 5 changes before we make it 6-5, in which case you become critical. So the definition of degree of responsibility was, roughly speaking, how many things did you have to change before you were critical? +1. So it's 1 over k +1, where k is the number of things you had to change to become critical. Qualitatively, it seemed that it was capturing a lot of what people care about. I'll say a few words about this later. That's responsibility. Blame is different. Blame, okay, so people use these words interchangeably. We needed to give formal definitions. Blame takes into account people's epistemic state. So think of a doctor who gives a patient a drug. The drug causes the patient, it has terrible side effects, and the patient dies. So the doctor is the cause of the death. He's responsible. Had he not done it, there's nobody else in sight who'd done anything. But let's say he had no clue that this drug had bad side effects. So we like to say, okay, we might not hold him to blame for that. So to capture that, we have a notion of uncertainty. That's where we bring in uncertainty. And there are two things you might be uncertain about. You might be uncertain about the way the world works, which is the model. What are the equations? You might be uncertain about what happened. That's the context. So you have a probability on pairs of model context pairs. And we can talk about, in some of them you're the cause and others you're not. We can talk about the probability of causality. And roughly speaking, your degree of blame is your expected degree of causality, expected degree of responsibility. Let me give you an example that will explain, I hope. Imagine a firing squad. So I'll get that in some approximation. With 10 excellent marksmen, only one of them has a live bullet, the rest have blanks. Actually, they do something like this, but it's usually 8 out of 10 have live bullets. And the intuition is that so they're all excellent marksmen, they shoot at the prisoner who does. Well, in this case, where only one of them has a live bullet, one of them is the cause, the one with the live bullet. Had he not shot, the guy wouldn't have died. That one who's the cause has degree of responsibility 1. He's critical. All the rest have degree of responsibility 0. But if I have no idea who has the bullet, so I place probably 1/10 on each of the people having the bullet. If I'm one of the people, my degree of blame is 1/10 because it's my expected degree of responsibility. My degree of responsibility is 1 with probably 1/10. It's 0 with probably 9/10. It's 1/10. So that's essentially the formal definition of blame is expected degree of responsibility, where the expectation is taken with respect to your probability on model context pairs, on what you think the world looks like. And let me just briefly say that in legal reasoning, what matters is not only what you did know, but what you should have known. So the formal definition defines blame relative to an epistemic state, these beliefs. It doesn't say what the epistemic state should be. So we can look at the doctor's actual epistemic state. He had no clue that the medication had bad side effects. But the law might say, well, wait a minute. There was a major study published in the New England Journal of Medicine, which is a major medical journal, that said, this medication has terrible side effects. You should have known. Or even worse, there was a little insert in the bottle that talked about side effects, which you didn't read because it said that this, you should have known, right? So the law might say that the appropriate epistemic state is the state that, a reasonable doctor should have had, right? And the reasonable doctor should have known. So as I understand it, when it comes to criminal liability, we look at the reasonable, we look at maybe the doctor's actual epistemic state, and we look at civil liability in the states. We look at the state that he should have had. But in any case, the definition is agnostic. It's with respect to a state. So with that, let me conclude. So, not terribly over time.
It's okay. Ronald's going to go in.
Yeah.
I'm going to
Okay. See you at 1, Ron. People have looked at this, and this is a talk in the computer science department. So people have looked at causality in terms of accountability. What's the cause of security breach? And they basically use our definition. In databases, you got a certain answer to a query. What was the cause of, which tuple in the database or which tuples in the database caused you to get that answer? What caused the network failure? In program verification, I love this story. My co-author, Hannah Trucknow, was looking at, which line of code caused a problem. So the program was incorrect. So standard model checkers will say, okay, program's not okay, but you might be really interested in, okay, so which line caused the problem? So that was degree of responsibility. She used our notion of degree of responsibility to get a useful definition in the context of program verification. She built a software tool when she was at IBM that sort of supported this notion. She took it down for a few days and all the software engineers complained they wanted their tool back. So, apparently it was actually useful in practice. Let me not talk about complexity in the interest of time, but I don't have it here, but let me talk about experiments, right? So the trouble with people. So technically it was Josh Tenenbaum, Toby Kristen Felt, and me. Person really did all the work was Toby. Toby at the time was a postdoc with Josh Tenenbaum at MIT. He's now a professor of psychology at Stanford. And we were trying to understand, he was actually the one who authored these experiments in soccer to see would the temporal ordering make a difference. And we were trying to understand the degree of responsibility in voting scenarios. So, if it's a 4-0 vote, to what extent is each voter responsible, 3-2 and so on. So qualitatively, our definition of responsibility was doing well, but it turned out normality mattered. So Toby had this one, it was great. We did this at Amazon Turk. We would talk about it, and then he called me back 2 hours later and said, I got the results. Never used to happen like that before, right? I remember all these stickers on elevators where you say, if you want to participate in the experiment, we'll pay you $10. Now it's none of that stuff. It's all Amazon Turk. So we did this experiment on to what extent were you responsible for various voting scenarios. And we were trying to take into account normality. So Toby had this great idea that we say, okay, we have Republicans and Democrats. And this is a bill, the Republicans all support, the Democrats all hate. The vote was 4-0, but one of the Democrats voted for it. To what extent is everybody responsible? And the Democrat was viewed as far more responsible than the Republicans because he was being abnormal. Normal would have been to vote, because the party said vote against and he voted for, right? So if you remember all the discussions where Joe Manchin was the critical vote and he was viewed as being responsible for the various outcomes. Well, what about all the Republicans who voted, right? He was only, but they didn't count because they were just voting the party line. So people clearly, when they're judging degree of responsibility, are taking abnormality into account. And these experiments were really demonstrated in a very nice way. And let me just conclude with a story due to Denis Hilton, actually, Dennis Hilton, but he's in France. Denis Hilton. Depending on their focus, so we're interested in, what's the cause of a traffic accident? So, a guy was driving, he had an accident, what's the cause? The engineer might say, oh, bad road design. The mechanic might say, lousy brakes. The sociologist might say, oh, there's a pub near the highway, he drank too much, and that's why the accident. Psychologist might say, oh, he was depressed. He broke up with his girlfriend. That's why he went to the pub to drink. That's why he had the accident. Now, these are all reasonable answers. And the way we would model the difference, basically, is what are you taking to be exogenous and what are you taking to be endogenous? So typically, what we take to be exogenous are things we can't control. What we take to be endogenous are things we can do something about. We care about causality to the extent that we want to understand the world better and change things in the world to get desired outcomes, right? So the engineer feels like I can do something about the road design. I'm going to make that endogenous. The pub, that's exogenous. It's just there. What can I do about it, right? Whereas, the psychologist might take as endogenous had he gone to treatment, he wouldn't have been so depressed. The state of mind of the driver, and take the road design as exogenous. So there isn't a right answer or a wrong answer. My point is that the way you model things depends in part on what you feel like you can control. And let me just conclude by saying that, look, even if people shoot down this definition tomorrow, I still think the definition is useful. And what's really nice is I think mine was the definition. So this whole idea of causal models turns out to be really interesting and useful. We've used it to define blame and responsibility. I mentioned that in the talk. Also explanation, blameworthiness, which is different from blame, intention, and actually very recent research, like a paper coming up in ICHI, one that was just in NERPS, using it to define harm. What does it mean that this action caused harm? Which turns out to be a big deal because, like, the AI draft document, the European draft document in AI uses the word harm like, 35 times. And then somewhere they say, it would be good if we had a definition of this. And it turns out that the philosophy community tried to define it. And there's this paper, which I personally found really annoying, that said, harm is I quote, Frankensteinian jumble. We can't get a good definition. We shouldn't try to use it. We should use other notions. Well, so this paper understood that you need counterfactuals because there's a causal notion going on here, and was totally oblivious to the stuff I'd done with Pearl, which got me annoyed, which would have solved half their problems. The other half involved using a default. I'm happy to talk more about that, but let me stop at this point. I've already abused you enough. I'm over time, and you're back. You missed all the good stuff. I'm happy to answer questions, and as long as if you feel you need to leave, feel free to leave. But yeah.
In your transitivity example, it required quite contrived sort of setting, and
So
I'm wondering that maybe we believe cause and effects are transitive because in most natural scenarios,
I think that's right, and that was I told you I had a paper that gave sufficient conditions for causality to be transitive that was trying to capture that intuition, saying, look, as long as these conditions hold, and they hold in a lot of standard scenarios, then you get transitivity. So I actually have a paper that formalizes that. But I will say that it's once you understand how you go about constructing accounting center, things like homeostasis, that the propensity of natural systems that try to bring things back to a stable state. In homeostatic systems, they turn out to be not at all contrived. They happen in the body, where if you do something, it will come back and if it gets really hot, you sweat, so you keep your body temperature normal. It turns out that you get these examples of causality being not transitive. So it's not quite as weird as you might think, but I actually agree with your intuition that in general it is transitive. Yep.
Yeah, so you mentioned this degree of responsibility and also this effect of combination of variables. So that brings me to this thought: how much is Shapley value used in this?
So that's really interesting. So I had a conversation with Saki Gaboa, who's an economist. So we did not use Shapley value, but we could have. And so over dinner one night at a conference, Saki and I sketched out the definition of degree of responsibility that use Shapley value. For those who don't know, Shapley value is a way of basically assigning blame in economics, or assigning responsibility, and you get a payoff to the extent that you're responsible for an outcome, very loosely, in a cooperative game. And I think it would have worked. Qualitatively, it would have been more or less similar in spirit. The fact is, this qualitative definition. So I'm not saying that the degree of responsibility is really 1/6. So when I say that when we did these experiments in Amazon Turk, qualitatively it seemed to be supporting our definition, but numerically we weren't getting exactly the same numbers. So Shapley value would give you numerically different numbers. I decided in the end that it wasn't worth the finer grain that you get out of Shapley value, but you absolutely could define degree of responsibility using Shapley value. It would, and I should say that I have a definition of blameworthiness. And when we talked about, I have a paper on group blameworthiness where we did use Shapley value, paper I wrote with a student, Mary Friedenberg, and the intuition was you had a whole group of people, and what they did resulted in a certain outcome. To what extent is each member of the group to blame? And there we use Shapley value to allocate. So we had, our definition gave us how much should you blame the group as a whole, and then we allocated joint individuals in the group according to Shapley value. So we used it in that paper in a slightly different context, but somewhat related. Yep. One more coming.
Just one quick follow-up. I'm not familiar with this literature, so is there anything interesting about the negation of causality, like prevention rather than causality?
Yes.
Or does it fall in the same framework and you just change variables?
Well, in our definition would fall in the same framework, but there are experiments by Steve Sloman and Claire Harris, a psychologist, that show that people, when you use the word prevention rather than causality, they don't quite treat it as negation of causality. I mean, so words, spark connections in people. So what can I say? Our definition would treat prevention as the negation of causality, but people don't. I haven't looked carefully enough, but I can definitely say that there's at least one psychology paper that will show that at least not people. What's more?
I'm trying to think of a serious question, but the original question was about, what would ChatGPT have answered for these? And then I wanted to turn that into a serious question.
I think there, to what extent, I mean, for me, the serious question would be to what extent does ChatGPT understand causality?
Well,
People started looking at that.
Yeah.
And apparently the answer, so again, don't quote me on this, I haven't been following literature
Yeah.
that carefully, but it definitely does understand causality.
I was wondering whether, I guess, I'm trying to
At
make
some point.
that a bit more serious. So I was
Right.
thinking, like, you've got your sort of black box
Right.
models. If you could somewhat model the outcomes, I'm guessing you would probably get different sorts of notions applied to different examples that might
Yeah.
be similar. Like, it might not be consistent. It'd be interesting whether it's consistent in some sense or not.
What I hope will happen is that certainly sometimes people will give different examples. And in the ideal world, I'll be able to say, okay, they're just working with slightly different models. So in model 1A is a cause of B and model 2A is not a cause of B. And what explains the fact that people are giving different answers is that they're using different models. And sometimes that's fairly clearly the case, maybe not always. So with ChatGPT, I mean, it probably doesn't understand causal models. I don't think it's at that level, but it might be the case that we could understand what it's doing is, in some sense, what its prediction model is doing is it's predicting a certain model.
But it would be interesting to see if it's somewhat systematic.
That
So I'm
would,
guessing that
yeah. So I
less.
have a paper that I'm carrying around that's looking at causality in ChatGPT. So I might be able to say more about this if I get a chance to read this paper. It was just posted in archive a couple weeks ago.
Can I just not have my own, sorry,
Okay,
I don't know.
I just got some online questions as well. So go
Just to follow up on that comment of noise, it's not clear whether ChatGPT actually has a theory behind when it does that, or whether it uses purely what it goes and collects. So it will not actually do any theoretic.
No, I suspect it doesn't have a theory, but it's doing prediction based on all the stuff that it's ingested and so, I mean, does it have a theory? Maybe not, although maybe one is somehow encoded in the prediction space. It's clear, you ask people about causality, they have very strong intuitions in many cases. They do not have a formal theory. I'm not trying to suggest that. So this does seem quite analogous to ChatGPT. It's in some sense acting like people. What's it basing its answers on would be interesting to understand. Because it's hard, when you look at people, why are you saying that A is a cause of B? And I mean, I'm not sure exactly what people would say. Again, I don't think they have certainly you don't have a fully worked out theory. But people do have strong intuitions. They're clearly based on something. I mean, don't push me too hard. I mean, I'm not a psychologist, but so definitely, I mean, I talked a lot to Toby Gerstefeld, who is a psychologist, and he can show that definitely they're thinking to some extent counterfactually, because he has experiments where he's tracking people's eye gaze. So in sort of billiard ball settings where, this ball hits this ball and that causes it to go here. And when he asks the questions about causality, he's looking at their eye gaze and what they're tracking. He can make a fairly compelling argument that they're trying to figure out certain counterfactuals. So to some extent, they're thinking counterfactually. Not always. There are other theories where they talk about, if I punch you and that causes you to knock over, there's some sequence of events where things are being transmitted along the sequence. Don't push me too hard in this. But they're not thinking counterfactuals. So not all definitions of causality involve counterfactuals. There's a regularity theory that, what's happened many times before and what's different, and that's the cause. So, what are people using is probably some combination of the above, I guess. But Ron, I'll let you figure out the next question.
So it's online.
Right. Well, so we had one more here. Maybe we can do that.
Serious question then. So look, Pearl is famous for invading networks, but telling us that the links don't mean, they mean influences, called direct.
Well,
Like
formally they don't mean influences, they mean probability.
Well,
It's when he interpreted them as influences that he got to causality. And the history is that the folks at CMU, Peter Spiritus and Richard Shines, who had been working on a system called Petrad, which was a graphical model of causality, basically convinced Pearl that he should think about causality and not just the pure probabilistic statements. And for over 20 years now, Pearl has been working on causality. He has a couple of books out, but what the cause of the switching, so basically he reinterpreted Bayesian networks causally.
non-Bayesian. non-Bayesian link.
Yes, okay, that too.
So that's my question, though, was about the nature of those links. So you said, think of them as direct causes. Well, that sort of begs the question of what's direct cause. But also your other link, the one between Susie and Billy, that says that Billy's didn't hit the thing.
Right.
That doesn't seem like a direct cause of anything. It's something temporal or something else, or is it all the same?
Well, so, I mean, Pearl is a bit, I mean, it's a fair question. Let me try to answer it. So if I think about Susie and Billy, there's just equations. So I do think of the equations as modeling causality. I mean, if you're asking me, I do. It's not enough. I mean, you might say, well, haven't you already solved the problem now? And well, no, because if I had, it wouldn't have been so complicated to even talk about Susie and Billy. And even in that question, why is Susie a cause and not Billy? Even though I have the direct links and even though I'm interpreting them causally. But I would say, look, Billy hits, at least in this sort of mechanical model where Susie throws first, what determines whether or not Billy's rock hits the bottle? Well, in this model, it's whether he throws, obviously. If he doesn't throw, can't possibly hit it. And also whether or not Susie's hit the bottle ahead of him. So, and if she has, there's no bottle there to hit. So I would interpret that the fact that Susie hits is causing Billy not to hit, at least in some reasonable sense, the word causality. I do interpret that causally. So I'm happy to talk more offline. Let me allow Ron to.
But the first online question was actually, do you differentiate between a cause and influence? If so, how?
So as I said, with the direct cause and in the equations, I do think of each of the parents as influencing the outcome. And I, roughly speaking, I think of them as a direct cause, so I'm not making a big distinction. But when I look at the more general question of, did Susie's throw cause the bottle to shatter? There, I mean, yeah, it influenced whether or not the bottle shattered, but there it seems the distinction is a bit greater. I mean, did Billy's throw influence that? So I guess at some level, I mean, I would not call A a cause of B if somehow the fact that, I wouldn't call A equals 3 being a cause of B equal 1 if the fact that A was 3 didn't somehow influence the fact that B was 1. But the influence is a bit tricky because you can get, again, think of Susie and Billy, that in the story, the bottle would have shattered even if Susie hadn't thrown. Right, so does Susie's throw influence the final state of the bottle being shattered? Well, the usual intuition for influence is that, she could have affected the outcome. Had she not thrown, the outcome would have been different. And in fact, given that Billy threw in the actual circumstance, the outcome would not have been different. So you have to sort of look at the counterfactual circumstance where we consider what happens if Billy didn't throw to reveal the influence. So that what that says to me is that whether or not Susie's throw influenced the outcome that question's a bit more subtle than it might seem at first. So is that the same as causality? You better tell me first what you mean by influence, which I don't try to define.
Okay, the next question says, it seems to me that making the temporal dimension implicit instead of making it explicit, as in temporal logic, is the reason for some of the challenges with counterfactual causality.
I disagree that it's the reason. So we can give a model, for example, with Susie and Billy, where the variables are time-stamped. So we absolutely have the temporal stuff. Now we get, of course, the expected answer. We actually saw it as a feature that you didn't necessarily have to introduce time. I'm perfectly happy to introduce time. In fact, one of the things I'm working on now, which turns out to be not completely trivial, is combining causality with the runs and systems framework that I introduced in the work on knowledge that has quite explicitly time and epistemic state encoded, and I want to add causality to that. So I'm certainly quite comfortable with adding time, but let me at least say I don't think the fact that we didn't have it explicit here caused any of the problems that they were sort of there anyway. At least my 2 cents.
Okay, and the final question, do you think causality can be learned by probability models if the model is sufficiently large?
Ooh, good question. I think the formal technical answer is no. So the question is, let's say from statistical information, can you learn causal information? And Pearl has a bunch of theorems where he gives sufficient conditions for which that's true. So that is to say, so here's how I interpret the question, which might not be how it's meant. Can you learn purely from statistical information without performing interventions what the causal relation is? And as I said, there the technical answer is not in general, because there are examples of, for example, two different causal models that both might have the same statistical information and you can't distinguish between them. And Pearl gives such examples, right? And he gives sufficient conditions where you can learn causality from statistical information, but they don't always apply. So the formal answer is, at least as I understand the question, is no. But I think you can learn a fair amount. And if you had sufficiently rich models that sort of looked at all the that sort of essentially model all the possible counterfactual situations there, you had information about that, then maybe the answer is yes. But again, think about, we want to understand the effect of introducing mosquito netting, does that affect the rate of malaria? Well, if it never had been done before, and you want to see, well, and what's the effect of charging for it? Well, nobody had ever done that before. We have no statistical information. So the model just doesn't give you what you need to know to understand the effect of the intervention. So,
Okay, question from me.
okay.
What work is the notion of causality supposed to do in the case of the blame assignment? We could sort of say that, okay, that the work that the causality definition, together with whatever sort of policy settings we've got, does for it is to help us decide who goes to jail, right, which then sets up a utility function that generates behaviours in society. But for engineering purposes, is there a sort of...
So I would say the same kind, so we want to understand the causal model in general, because we want to understand what we could have done differently to change the outcome. And that might affect future policy. So it can be both retrospective. If you think of a breach, you want, who do you blame for what happened? But it can also be prospective that, all right, the breach happened. We want to make sure it doesn't happen again. What can we change to make it different next time to make sure it doesn't happen? And again, you'd need a causal model for that. So, so I think, we care about causality, and it's clear. I mean, all these experiments by Alison Gopnik, who's a psychologist on children, and she talks about children being little scientists, and what she's mainly focusing is on the fact that they want to understand causality, right? I'm looking at my own kids, especially one of them, I really see it. Pressed every single button to see what effect it would have. Well, why do we care? Why do kids really care? And presumably it's evolutionarily adaptive that we learn about these things. Why? Because if we want to affect a certain outcome in the world, what do we have to do it? If we understand the causal connections, then does doing a rain dance cause rain? Well, we want to know that there's a drought. Should we do a rain dance? Are we going to get rain? Right? I mean,
there's no control.
Well, we do. Well, yes, we do. We do want control, and in order to get control, we have to be able to predict the future, and the prediction might not be purely statistical. We care about causal prediction. If we do this, this is what happens next. So, yeah.
Okay, at this point, I want to ask a question about quantum causality.
Oh, no. Sorry.
It's a whole lot of rabbit hole.
Yeah, about which I have nothing to say. So I'm not just.
Okay, so that's.
Yeah, I'm sticking around. I'm not going.